Lecture problem 4. A solid disk that has a moment of inertia that equals 1/2 mr squared is released from rest at the top of an incline, starts to roll without slipping. The inclined plane is 15 meters long and makes an angle of 30 degrees with the horizontal. A. What is the speed of the disk at the bottom of the incline? B. What is the magnitude of its acceleration? The first thing that we need to do is to sketch a free body diagram. There are three forces acting on the sphere. The normal force is acting perpendicular to the surface of contact. The weight mg, which acts straight down. And finally, the static friction force, which acts upward parallel to the inclined plane. Notice that the only conservative force is the weight mg. The normal force and the friction force are both non-conservative forces. The normal force is always perpendicular to the displacement while rolling down the incline. Therefore, the work done by the normal force is going to be 0. Write it down on the side here. The work done by the static friction force, as stated earlier in one of the videos, always does 0 work. Therefore, the work done by the non-conservative forces is going to equal 0. As a result, the mechanical energy of the system is conserved. KE initial plus PE initial is going to equal the KE final plus the PE final. Notice that the kinetic energy comes in two different forms. The translational kinetic energy 1/2 mv initial squared plus 1/2 I omega initial squared. The potential energy comes in one form only, which is the gravitational potential mgh initial. That equals the kinetic energy final in two forms also, 1/2 mv final squared plus 1/2 I omega final squared plus the gravitational potential energy mgh final. Since the disk starts from rest, both translational and rotational kinetic energies are going to be 0. If we choose the height final to be the bottom of the incline to be 0, therefore the potential energy final is going to be 0. And this equation is reduced to the following. mgh initial equals 1/2 mv final squared plus 1/2 I omega final squared. The height initial can be easily solved for using the length of the inclined plane, which I'm going to call d. Sine the angle 30 is going to equal the opposite, which is the height initial divided by the hypotenuse, which is d. Solving for the height initial, you obtain d sine 30. Now let me detail the equation a little further. mgh initial can be written down as mg. Instead of h initial, I'm going to substitute it by d sine 30. This is going to equal 1/2 mv final squared plus 1/2, the moment of inertia is equal to 1/2 mr squared times omega final squared. And we know that the omega is related to the linear speed by means of the following relationship: v final over the radius of the disk. Therefore, omega final squared is going to be v final squared over r squared. Notice that the mass is a common factor, therefore is going to cancel out. The r squared is going to cancel out here also. And the equation is now GD sine 30 equals 1/2 V final squared plus 1/4 V final squared. Simplify it even further. GD sine 30 equals, the common denominator between the half and the quarter is 4. Therefore, the sum of the half V final squared plus 1/4 V final squared is 3/4 V final squared. Isolating the V final squared, we obtain 4/3 GD sine 30. Square root both ends, we obtain the V final to equal square root 4/3 GD sine 30. Solving numerically for the V final, we obtain 9.9 meters per second. To solve for the acceleration of the disk, there are many ways, but since the initial and the final speeds are known to us, it's better at this point to use the kinematics. The V final squared equals the V initial squared plus 2 times the acceleration times x minus x0 relationship. The distance d is equal to the x minus x0 in this case. Therefore, this equation can be simplified as follows. V final squared equals, the V initial is 0, therefore V initial squared is 0, plus 2 times the acceleration times the distance d. Isolating the acceleration, we obtain V final squared divided by 2d. Solving for the acceleration, we obtain 3.27 meters per second squared.